I'm selecting the best algorithm to shrink my 100-feature dataset down to just 2 features for easier visualization. Think of it like taking a really complicated 3D map and making a simpler 2D version. My data has 100 different characteristics for each data point. That's a lot of information to handle. I need to find a way to simplify it. I want to create a 2D plot that shows my data. This helps me to see patterns and relationships between data points easily, which would be impossible with 100 features. Sklearn provides several tools to help me do this. Isomap is a powerful technique, but it takes a while to run because of complex calculations. However, it's perfect for data that is nonlinear and has a complex, overall shape, global structure. Think of it as making a map that accounts for curves in the road, unlike a flat map. LLE is good when the data is locally linear. That means each tiny part of the data looks like a straight line. However, the entire dataset doesn't have to be perfectly linear. T-distributed stochastic neighbor embedding, T-SNE, is great for visualization, but it's not known for its speed, particularly with lots of data. So, that statement is not entirely accurate. Multidimensional scaling, MDS, is primarily designed for linear data. While some variations can deal with nonlinear data, basic MDS isn't ideal for that. I'm choosing the best dimensionality reduction algorithm. This involves picking the right tool for visualizing high-dimensional data with lots of features, in a simpler, two-dimensional space. We'll be looking at algorithms suited for this purpose from the Sklearn library. We have a dataset with 100 features, way too many to easily visualize. The challenge is to find a way to see patterns in this high-dimensional dataset using only 2 dimensions. We suspect that the underlying data structure is actually much simpler, living in a lower dimensional space. This is where dimensionality reduction techniques come in handy. We'll evaluate several dimensionality reduction algorithms from the Sklearn library to see which are best suited for our high-dimensional data. We'll assess each algorithm's strengths and weaknesses to find the ideal fit. This statement says that T-distributed stochastic neighbor embedding, T-SNE, is faster than Isomap. I need to check if this is accurate. T-SNE is excellent for visualization, but it is computationally expensive, especially for large datasets. This is often the case with high-dimensional data. Locally linear embedding, LLE, is a good algorithm, but it's better suited for data that has locally linear structures. A globally smooth manifold is a little different. I need to consider if this statement accurately reflects LLE's characteristics. Isomap, isometric mapping, is computationally intensive, meaning it can be slow. However, it's fantastic for visualizing data with complex, nonlinear relationships across the entire dataset. A global nonlinear structure. Multidimensional scaling, MDS, is a dimensionality reduction technique. Classical MDS, however, primarily handles linear relationships, not nonlinear ones. There are other, more advanced forms of MDS that can handle nonlinearity, but the basic form isn't ideal for this. I see TSNE, T-distributed stochastic neighbor embedding, as a powerful tool for visualizing high-dimensional data in 2 dimensions. However, remember that it's computationally expensive, especially with large datasets. Think of it like trying to arrange a massive group of people based on their similarities. It takes a lot of effort. Isomap, isometric mapping, is another dimensionality reduction technique that I find particularly useful for datasets with a globally nonlinear structure. This means that the underlying relationships in the data aren't simple or linear, they're curved and complex. Imagine trying to unfold a crumpled piece of paper. Isomap is like finding the shortest path between points on that paper to get a clearer understanding of its true shape. But, be aware, it is computationally expensive. Locally linear embedding, LLE, is great for data that sits on a locally linear manifold, meaning the data points are linearly related to their closest neighbors. Imagine a curved surface. LLE focuses on small, relatively flat sections of that surface at a time. It doesn't try to understand the global shape, only the local neighborhood. Multidimensional scaling, MDS, is a versatile technique, but in its classical form, it's primarily suited for linear dimensionality reduction. Think of it as simplifying data by representing it in a lower dimensional space while preserving the distances between data points. However, variations exist that can handle nonlinear relationships. This means we have data with 100 different characteristics for each data point. The goal is to reduce these 100 dimensions to just 2 for easier visualization without losing crucial information. We need to carefully choose the right dimensionality reduction algorithm, t-SNE, isomap, LLE, or MDS, based on the nature of our data and the balance between computational cost and the accuracy of the resulting visualization. The final aim is to create a two-dimensional plot to visually represent the high-dimensional data, allowing us to observe patterns and relationships that wouldn't be apparent in the original 100 dimensions. That's the magic of dimensionality reduction. I'm choosing the best algorithm to shrink my 100-feature dataset down to just 2 features, making it easier to visualize. I need to consider each algorithm's strengths and weaknesses to make the right choice. My goal is to create a two-dimensional plot of my data, which will let me see patterns and clusters much more easily than with 100 features. Think of it like taking a complex 3D object and flattening it onto a piece of paper. We lose some detail, but we gain a clearer overall picture. I have a dataset with 100 different characteristics for each data point. That's a lot of information to deal with. Dimensionality reduction helps me simplify that. T-distributed stochastic neighbor embedding is a powerful technique, but it's computationally expensive, especially with large datasets like mine. It's great for revealing clusters but is slow. Isomap, isometric mapping, is another excellent option, especially if my data has a curved, nonlinear structure. However, it's also computationally intense for large datasets. It's good for capturing the global shape of the data. Locally linear embedding is a good choice if the data points locally resemble a flat plane. It's more efficient than t-SNE or isomap but might miss the bigger picture if the data is globally curved. Multidimensional scaling. The basic version handles linear relationships well but doesn't cope so well with curved data. It's relatively efficient. I'm choosing the best algorithm to shrink my high-dimensional data down to just 2 dimensions, making it easier to visualize. Think of it like flattening a crumpled piece of paper. We want to see the overall shape without all the wrinkles. I need to carefully consider which method is best suited for the task. Let's dive in. I have a dataset with 100 different characteristics or features for each data point. This is like describing a person with 100 different measurements: height, weight, shoe size, and so on. It's hard to visualize or work with 100 numbers at once. I need to find a way to reduce this to a more manageable number, ideally 2, for plotting on a graph. I'll select my algorithm based on how my data is organized. Is it neatly organized, or is it a bit messy? Does the relationship between data points follow a simple linear trend, or is it more complex and curved? This will guide my choice. t-SNE, T-distributed stochastic neighbor embedding, is great for visualization, but it's computationally intensive, especially with lots of data and high dimensionality. It does a good job of preserving local neighborhoods, meaning nearby points stay close together after the reduction. However, it can struggle with very large datasets, and global structures can be distorted. The trade-off is that the visualization often looks nicer than what some other methods give. LLE, locally linear embedding, works well when data points have local linear relationships, meaning that points are linearly related to their neighbors. Think of it like fitting small, straight lines to tiny parts of the data. It doesn't do so well if those local lines have to be connected in a globally curved way. Isomap, isometric mapping, is powerful but slow. It's ideal when the data has a complex, curved, overall structure, a global nonlinear manifold. Isomap finds the shortest paths between points, even if they appear far apart when looking only at direct distances. Imagine it as unfolding a crumpled map to reveal the true distances. MDS, multidimensional scaling, is often used for linear dimensionality reduction. While there are extensions that can handle nonlinear data, the basic version only works well for linear relationships. It aims to preserve the distances between all points in the lower dimensional space. The best algorithm depends on the data. I need to carefully consider which algorithm's strengths best match my data's characteristics. This is like choosing the right tool for the job. My final goal is a simple 2D plot that shows the essential structure of my high-dimensional data. This allows me to visually inspect clusters, patterns, and relationships that were hidden before. I find ISOMAP computationally expensive because it calculates all pairwise distances between data points and then uses spectral decomposition, a fancy way of saying it solves a specific type of equation using matrix math. However, it's amazing at revealing the underlying structure of data, especially when that structure is globally nonlinear. Think of it as a curvy, not straight, path through the data. It's like finding the shortest path on a curved surface, not just a flat one. I'm choosing the best algorithm to reduce the number of features, from the original 100 to just 2, for easier visualization. This helps us see patterns that might be hidden in the high-dimensional space. I'm working with a dataset having 100 different characteristics for each data point. This high dimensionality makes visualization difficult, but dimensionality reduction techniques can help. I want to plot my data onto a 2D graph, which is much simpler to interpret than a 100-dimensional space. That's the goal of my dimensionality reduction work. LLE, or locally linear embedding, is great for data points that are locally linear, meaning they form roughly straight lines within small neighborhoods, even if the overall data structure isn't globally linear. It's like looking at a curved road. Each small section might seem straight, but the overall road is curvy. MDS, or multidimensional scaling, is a dimensionality reduction technique. Classical MDS primarily focuses on linear dimensionality reduction. Think of it as finding the best way to represent data points in a lower dimension while keeping the distances between points as similar as possible to the original high-dimensional space. There are variations that can handle nonlinearity better. T-SNE, or T-distributed stochastic neighbor embedding, is really good at visualizing clusters of data points in a lower dimension. However, it's very computationally intensive, meaning it takes a long time to compute, especially with large datasets. I'll have to consider that when choosing my algorithm. I'm selecting the best algorithm to shrink a dataset with lots of features, like 100, down to just a few, making it easier to visualize and understand. Think of it like making a complex 3D model into a simple 2D drawing. This means I have data with 100 different characteristics for each data point. It's like describing a person with 100 different measurements, height, weight, shoe size, and so on. It's hard to work with so many numbers. TSNE, T-distributed stochastic neighbor embedding, is one algorithm that I can use. It's great for visualizing high-dimensional data, but it's computationally expensive, meaning it takes a long time to run, especially with many data points. ISOMAP, isometric mapping, is another option. It's good at finding the underlying structure in data that's curved or nonlinear. However, like T-SNE, ISOMAP is also slow for large datasets. LLE, locally linear embedding, works best when data points are arranged linearly in small neighborhoods. It's not great at capturing global, curved structures in the data. MDS, multidimensional scaling, is a simple method. Standard MDS deals primarily with linear data. It's not as effective with data that has a complex curved shape. Some algorithms, like T-SNE and ISOMAP, need lots of computing power and time. This describes data that has a complex, curved structure, not just a simple straight-line relationship. This refers to data that is locally linear, meaning it looks like a straight line when you zoom in close enough on small sections of the data. This means the data follows a straight line pattern. It's a simple relationship between the variables.